Hi, I'm Lynn, and I'm back with part 2 of the Brain2Pix guide, where I will talk about how to pre-process the brain signals. So in the previous video, I talked about how to prepare these Doctor Who frames in order to make the targets for the gun-like model. Here, I will talk about how to convert these raw brain signals and map them onto the visual space using the data that is provided in the Doctor Who dataset. So I opened up a Jupyter Lab here, and I will go through the 3 different files that I made in order to go from voxels to RFS images. So the first one is this notebook file. It's called NII to NP. The second file that we'll need is the SafeBrainRF Python file, and we need the align signals file. So first, the NII to NP file. So first we want to convert the files that these raw signals are in to become Numpy files. And you can do this with this code. I'm going to run this code and then show how the data looks like before and after. This is the directory to the data. In this case, this is the raw data, and there's only one run in this folder for storage purposes, but in the entire dataset there should be 121 runs. So keep in mind this is just as an example. And test, it's just a MATLAB file. Here we define the different directories to the raw data. This is the path that we want to save the data in as NumPy format. Okay, so the first loop is for the test set, and the second loop here is for the training set. So let's first look at the testing set, where we load in one MATLAB file and save the data in separate runs as NumPy files. When we load in this MATLAB file, so the MATLAB file for the test set is a dictionary with different items. In order to see what items are in here, we should look at the keys. We want to specifically extract these values because these represent the averaged brain signals in different runs. So mean 1, these are the brain signals for the first run. So if we want to save the brain signals of run 1, we should take the values by doing this. These are the run 1 values. And if we want to see how it looks like, this is the shape of the run 1 values. Here we can see 91 are the timestamps, so the time dimension. And then the other 3 are the voxel dimension. And what we want to do is save these in separate runs. And for the training set, we want to do the same, but they are saved in Nifty files instead of MATLAB files, so you can also visualize that. If we just say the run number is 1. So right now we have this file, which is a run 1 train file. It's a Nifty image. We want to convert it to become NumPy, which can be done by doing .data obj and then throwing this into NumPy array. Let's give this a name, run 1. So we have run 1 train NP, which is now the shape of this. And as you can tell, the dimensions are mixed up compared to the testing data set. And we want the time dimension, which is this, to be in the first dimension. So we can just do that by transposing the data and taking the time dimension, which is the third in this case, to shift it to the zeros. Oh, I don't know why I put transposing. I meant transpose. And now we can continue with this data. So we just save this in the directory that we want and then continue with this data from here on. So now we can also take a look at how the data looks like. Let's just clean this up. Okay, so for example, we have the test data, which is again this thing. It's taken out of this loop. It's just the last run basically, and it has 266 time points and this many voxels. And if we take the mean of this, the mean looks like this. And we also know that this is already normalized. Now let's look at the training data. trainbrain.mean. So the mean of the training set is quite a high value, and we also know that this is not normalized yet. We need to keep in mind that we still need to normalize the training data. So we will do that in the next steps, but for now this first file is covered. So the second code that we're looking at is called SafeBrainRF. And this code basically has two functions, the getRF function and the SafeRFs and signals function. So the getRF makes the mask for the receptive field images. So basically it takes the different retinotopic mapping centers and then it makes a 2D image from each receptive field center. So for each receptive field, it maps itself onto a 2D plane. So the second function called SafeRFs and signals takes the brain signals that we converted earlier to Numpy arrays, and it performs a z-score on the training set, and it takes away all the nons from both the testing and training, and it saves the signals separated by brain region. I will just run this in Jupyter Notebook again, and then it will become a bit more clear. Call centers. Looks like this. It is a dictionary with some items, and we want to see which items are in here. So we have different brain regions in this MATLAB file, and if we want, for example, V1, we want to take V1V and V1D. So V1V is the ventral and D is dorsal. Let's see how V1V looks like. You can already see here some nons, but let's see. What this means is that it has 747 centers. So if we were to print out the row centers, it should have the same shape for the same brain region. We can kind of see this as like x coordinate versus y coordinates, and we can make use of these coordinates to plot the centers on a 2D image. So that's basically what we do in the first function. So we select the brain region for the column and the row centers. Then we take away the nons. Then we stack these two centers together. This becomes the centers, basically. Here we make blank images with the size of what we specify. So in our case, it would be 96 by 96. This is ultimately the size of the input to your model. And these are the amount of receptive fields present in that specific brain region. So if we select here, we select V1V, then it will be 747 here. Okay, so now we have a stack of 747 images with the size of 96 by 96. So we loop through these centers that we made, and then we activate that single receptive field in that corresponding image at the right location. For example, the first image from 747 images will be blank, with the exception of one pixel that is determined by these center coordinates. So we make use of this function in the next function. So this next function is to normalize the data and remove the nuns. We first make a new directory for all of this data that is going to be made. Then we load in the region of interest masks. We need this in order to localize the brain regions in the voxels provided. We make a boolean out of this mask in order to use it later. And this is making a list out of all the directories within the brain signals. If we're applying this to the test set, then this line should output a list of 7 directories towards the 7 runs. If we're applying this line to the training set, then there should be a list of 121 directories pointing towards those 121 runs. We're just doing this in order to count how many runs there are. So I'm going to run individual lines in order to get a better insight of the function. First, we need the ROI mask. So we load in the ROI, and then what we want is we want to specify a brain region from this ROI mask, because right now it looks like this. It's a dictionary with various items that we can select by specifying the keys. If we want to stick with just V1 ventral for now as an example. So basically right now we only have zeros and ones in this array, and we can convert it to Boolean so that it only becomes trues and falses. Now what we want to do is we want to make use of this mask to extract specific voxels that belong to the V1 ventral from the whole brain data. So now we want to load in the brain data. And this is just the brain data that we processed earlier or converted earlier from NIFTIF files to Numpy files. Brain, that's where all our brain data resides. And we have test, brain signals, run 1, Numpy. Here we have the brain data. Again, this is the time dimension, the number of frames for this specific run. So now we can make use of this V1V mask to take out the voxels from this brain data that are specific to V1V. Let's first look at the V1V mask shape. This one is the same shape as the amount of voxels in the brain data. So we can easily use this as a mask on the brain data by only selecting the voxel dimensions. So now we can say this is V1V brain data. Now we can see this number that we see here is the time dimension, and this one is the amount of voxels for that specific brain region. We have also seen this number before when we took a look at the receptive fields. Each one of these voxels have been localized in visual space. So let's take a look at the V1V receptive field mask. These are the receptive fields coordinates. It's also 747. So each one of these location points towards a voxel in this brain region, which we can use later on to map these voxels onto visual space. Let's get back to the second function where we were. Yeah, so this is how you make use of a ROI mask to take brain signals that are specific to that brain region that you want. We do this for every run, and we also take the Z-score if the data comes from the training set because, as we mentioned before, the training data is not normalized yet. And we also set all the nonce to zeros. Because this operation happens in place, I had to rename the variable. There's probably a better way to do this, but I just did it this way. So this function allows you to input either V1, V2, or V3, and then it loads in the ventral and dorsal version of those brain regions, and then saves them separately in different Numpy files, which later on will be combined. But at this point, the ventral and dorsal are not combined yet. And then here we save the brain signals, ventral and dorsal. So I've made some changes that I find more suitable, but it's not really important to mention. Yeah, so I've explained these two functions that are in this code, and I've also showed how the brain signals look like in between. So now that you understand what these functions do, all you have to do is call this function and it should be good. And then it expects brain region, set T, call centers, row centers, and size. So we want the V1 brain region, testing, dataset. We have already defined the column centers and the row centers, and we want size of 96. Okay, so the length of the directory is 0. So we know that it's not correct because we expect to have a length of 1, so something went wrong. This is supposed to point to the brain signals. Let's check. Okay, so this should work now. Yeah. So this is how you call the function, and this is what you should see in order to be sure that it works. So because this video has gone longer than what I expected, I will stop here and I will continue with the aligning signals file in the next video. Thanks.